So everyone, welcome to our webinar on VN2, the inventory competition. I'm extremely excited and happy to be here with this amazing supply chain planning community today. We have, of course, together with me, the 5 winning teams and individuals. We have our sponsors. We're going to have 1 hour and a half together. I think it's going to be super packed with very, very interesting content and models, ideas, and insights. It's going to be a great time to exchange and discuss what worked and maybe what didn't work and what these amazing competitors try for the competition. As we start, I'd like to thank the 3 sponsors. We have Fliber with Fabrizio. He already sponsored VN1. We have been collaborating on this kind of thing for quite some time. So please, a round of applause and cheers for Fliber. We also have Tim from Daybreak. We met with Tim, I think it was 2 years ago at a presentation in the US. Tim and Daybreak also agreed to support us for VN2. So if we have VN2 today, it's of course thanks to Fliber and Daybreak. I also personally, with my consultancy company, sponsored a bit VN2. So myself, Nicolas van der Put, with my company, Subchains. It's always a pleasure for me to, well, organize it and support it. So as we start, I'd like to give a minute for the sponsors to introduce their company, but also to explain how they see, how they do themselves demand planning and inventory planning. So Fabrizio, would you mind to explain us how you do that at Fliber and what do you do at Fliber?
Yeah. First of all, I would like to thank Nicolas. He's a force of nature, so important for the segment. I met him about, I don't know, maybe 5 years ago. And it's been a pleasure, Nicolas, to work with you. You're so important for this whole segment. Thank you for everything you do. Okay, so I'm not going to talk about Fliber. The websites work for that. You can go to fliber.com to see about us anytime. What I wanted to talk today is first the reason why I connected with Nicolas about 2 years ago about starting to have these forecasting competitions, and I decided to sponsor the 2 first ones up to now. And if he allows me, I'm going to sponsor all of them moving forward. And the reason is because we're dealing with something extremely hard, especially when you start trying to solve this at scale as we're trying to solve in Fliber. So if you're a consultant, you get the data and you process that data and you are able to work with a customer, get context and do all those things, it's already very, very hard. And in Fliber, we do that automatically. We connect to the sales channels and inventory systems and grab all that data, have to make sense of it, run AI transformer ensemble to try to generate good forecasts, then have a layer of data contextualization, have a layer of supply chain mapping, then run another model, which is an adaptive consumption model to try to create replenishment recommendations. So it's extremely hard to do all of that. And we cannot do it by ourselves. That's why I'm sponsoring this competition. I want to learn from the best and hopefully you guys can help me solve these problems. So yeah, the biggest issue we have is we try to solve this at scale for companies between $5 and $100 million in revenue, which is a segment that is not served. So yeah, learn more about Fliber, go to fliber.com. Thanks, Nicolas.
Excellent. Thank you so much, Fabrizio. Indeed, supply chain planning is super difficult when you have the time, when you can investigate, and it's even more difficult if you want to do this at scale automatically for your clients. Next, we also have Daybreak with Tim. As you will see, they have another twist on supply chain planning. Tim, you can give us a word.
Yes, I also want to thank Nicola for bringing this community together and congratulate all the winning teams. And this is an extremely hard problem. And thanks everybody for your participation. Excited to learn from you. So Daybreak is an 18-month-old Series A supply chain planning software company. We do use machine learning and deep learning and SAP models to do prediction. But the unique twist is that we're also building autonomous agents to be able to reason over those predictions and consume a lot of qualitative data and context that typically goes into the decision-making process. Because one of the things that we find so frustrating is no matter how good the machine forecasts are, if people don't trust them and they change them, then the companies don't get the benefit. So that's what we're focused on is building agents in addition to using the traditional, techniques. And we are focused on the largest companies, largest consumer packaged goods and retailers in the world. We typically do business with companies that are over $1 billion in annual sales. But great to meet everybody. If you want to learn more about Daybreak, go to our website or don't hesitate to reach out to me on LinkedIn. Would love to connect with you.
Thank you so much, Tim, for sponsoring the event and for sharing how you see supply chain planning. Now, I'd like to introduce you to VN2 before we discuss the winning solutions. So I know that most of you, I'm sure, took part in the competition, but I'd like to give a bit of a summary explanation to people who are not familiar with the data set and how this competition is different. So VN2 is the first inventory planning competition. We had in the past many forecasting competitions, but we never had an inventory competition. It's quite actually difficult to know if you have an inventory policy, an inventory model, if it's good or bad, because it's not just about doing one decision, it's about doing decision over and over. And that's what we tried to do in VN2, where participants had to place weekly orders for 6 weeks in a row, and they had to basically live with the consequences. So if they order too much or not enough in week 1, well, they will face these shortages or overstock for quite some time. So we really wanted to see not just models if they could work for 1 week, but if they could work over time and if these the decisions they took made sense. How did we do that? Basically, people had to play with 599 products. I guess I should have taken 600. It would have been more round, but it's 599. They had to place 6 weekly orders, so 1 week after another, and they had to balance or to minimize holding cost and shortage cost. So each time they had a unit in stock, they had to pay for it. And each time they faced a shortage, they also had to pay for it. Now, it was a bit confusing and difficult at first for many participants because we had a lead time of 2 weeks. It means that when you see your current inventory state, how much inventory you have today, and you make an order, you have to wait for 2 weeks before you receive it. So there is this question of lead times and horizon that the forecast you do, it's not just for next week, you have to see ahead what's going on. And this will be very important in the conversation we will have with the winning solution. Before we look at this solution, I'd like to discuss something with you. So for this competition, I wanted to bring a benchmark just to have an idea where if we do a simple model, how many people can beat this simple model and by how much can they beat it. But it's quite difficult to come up with an inventory benchmark model because such a thing does not exist. So I had to sit down and to think, okay, what is a very, very simple model and at the same time something that's, let's say, smart or elegant, but still very simple that I could use as just a benchmark to see how good the other solutions were. I'll explain you shortly how I did that. And as you can see on the screen, this benchmark ended up being number 26 on the competition. So only 25 teams could beat it. So the first thing I had to do for this benchmark is to come up with a super simple forecast. So initially I had in mind, well, I can just do an 8-week moving average. But as you can see on the data, it's quite a seasonal data set. You have obviously these huge peaks here and there, but then you have smaller peaks throughout the year. You have one here, you have it's again over there, over there. I mean, we have some seasonal peaks, right? So then I thought, what about we just compute seasonal weights at a global level, so in the simplest possible way, and just apply that to the moving average. The forecast looked like this. You see the result on the real tested, but of course, I didn't have access to this when I did the model. And as you can see, simply adding these seasonal weights adds so much value. The code is available, by the way. The total code of the benchmark is, I think, 50 lines of code if you remove the plots. Very easy. I didn't optimize any of that, by the way. It's a simple benchmark. If you want to improve on this benchmark, you can use the code and you can pick a better moving average horizon, try this out to pick maybe that I did 13 weeks, maybe 26 is much better, maybe 8 is better. I have no idea. And then I had to come up with again, a super simple inventory model. I just decided to say, well, the model will simply be a 4-week coverage target. So to place an order, I would sum up the forecast for the next 4 weeks. I would compare that to the inventory that was available, and I was just ordering the difference. And that was it. If you want to improve on this, for the sake of it, to try out some things, I would try to simulate different coverage and see if 4 weeks was optimal. I'm sure 4 weeks is not optimal. I never tried it out, but maybe you'll find that 3.5 weeks or 6 weeks might be best. I have no idea. Something else that could be better, it's a bit more advanced, but the issue with this net projection is that it does not account for current shortages. If you have very seasonal data, and we have seasonal data, and if you face shortages, we face shortages, ordering the next 4 weeks might result in overstock. I give you an example here. Let's imagine today you have a shortage, so you're really out of stock, and you want to make an order that's going to arrive in 2 weeks. If you order based on the rule I just said of 4 weeks, you will order 390 pieces. But of course, this is the end of the season, so 390 pieces, by the time you get it, it's way too much. So that's one of the issues of using the net inventory, and that's what I did for the benchmark. So another way to improve it, if you ever want to do it, would be to take into account a projection of the inventory. That's it for me. I'm glad that I could have a minute to explain the benchmark, but also how to improve it. VN2, I designed it to allow people to compete, to of course see what works, what doesn't work, but I also wanted it to be a learning opportunity. The dataset is quite small, so actually you can use it, you can play with it using Excel. So if you're not a data scientist, you don't have a massive computer, you don't have Python, you just have an Excel file and you just want to give it a try, the dataset is there. It's only 600 products. It's going to work in Excel. Just keep in mind that it's always easy to win the competition after the competition. The important part is, of course, to win the competition when we don't have access to the final data. Guys, that's it for me. I propose that we move on with the first team, the Frugal 5. I will stop sharing my screen so they can take over, and then we can listen to their model. As the team shares the screen, I'd like to add one thing. We will have a Q&A. After each presentation, I will take one question from the audience. I'm going to read your question and ask one question to the team. So after each presentation, we'll do a bit of a Q&A for a few minutes. So feel free to ask the question. I will review that and ask one question to the team.
Well, thank you for organizing this very interesting competition. We had a lot of fun. We are the Frugal 5. Though that turned out to be a bit of an over forecast. We work at Albert Heijn, the largest supermarket in the Netherlands, in the operations data science department. So we work on demand forecasting and various logistic optimizations algorithms. We currently don't work on ordering or anything related to replenishment. So this was a really interesting challenge for us to try. Our philosophy was to come up with a fully data-driven method without any business rules. So no minimum or maximum stock levels that we set beforehand and then tweak, no safety stock. And to take a probabilistic approach. So we forecast the probabilities for the various demands. And then based on those probabilities, try to come up with an order amount that minimizes the expected cost. So first of all, this requires a probabilistic forecast. It also requires a policy that can understand these probabilities for multiple weeks ahead and incorporate them into an order that minimizes the cost. And an interesting consequence is that safety stock is not an input parameter, but is actually a result. So if we have a large forecast uncertainty, then our method should naturally order a bit more. Also, if the cost of holding is low and the cost of missed sales is high, it should naturally put in a bit more safety stock. So for the remainder, I will first explain the policy, assuming we already have the probabilistic forecast, and then at the end, Ruben will explain how we came up with the forecast. So as a short overview to start with, an important property of the competition is that the stock has a lead time of 3 weeks. So whatever we order now will not affect the cost in the next 2 weeks. And so we only optimize it for the third week. We also don't optimize it for the weeks after because we will have another chance with a new order to correct anything that goes wrong in the weeks after. And then in the meantime, up to those 2 weeks, we have probabilities for all the various possible trajectories. For example, 5% probability to sell 10, then 2, and then 3, etc. And then based on those probabilities, we can calculate for every possible order what would be the expected cost in the third week. And then we simply pick the order to minimize this. So in a bit more detail, consists of 4 steps. The first step, we start with the current stock, which is known. And this includes what we had left in the previous week and what's delivered at the start of the week. And we have a probability of forecasted demand for that week. And then we simply subtract the two to come up with the probability distribution of the stock at the end of the first week. That's then used as an input for the next step, which is similar, but now the current stock for the next week is not a single number, but a probability. So then to calculate the distribution of stock at the end of the second week, we have to mathematically take the convolution of these two distributions. And the only assumption we make here is that the current stock and the demand are independent. Then the third week is very similar to the second week, only now we don't group everything, all the probabilities, or we don't group all the stocks below 0, so we allow to go negative. So then we calculate what we call the shortage distribution, which is how much stock we are short, assuming we order nothing. Then finally, we go over all the possible amounts we could order, and then given this shortage distribution, we calculate the expectation value for the cost in the third week. And once we have all those numbers, we simply pick the order amount that minimizes it. And an interesting consequence of this approach is that we can directly optimize for the cost function. So even if we'd had a more complicated nonlinear cost function, for example, with the whole cost squared or whatever, we could still directly optimize for that. But of course, it all hinges on having accurate and well-calibrated forecasts. So now Ruben will explain how we came up with those.
Yes, so probabilistic forecasting. Like Diederik mentioned, our take was if we can assign a probability to basically anything that could happen, then we're in good shape, because then the optimization is more or less trivial. So what does that actually mean? If you look at the bubble on the right side of the slide, it says that we are looking for to be able to make some sort of statement like the probability that we will sell 3 units of this product in this store is 4%, and then for all possible for all store product combinations and for all different possible number of units. So how do we go about this? You could take some sort of Bayesian approach if you feel sophisticated, but we are simple guys, and light GBM is our bread and butter, so to speak. So our approach was to estimate with different light GBM models different quantiles, 1%, 10%, up until 99%. And these were just separate models, really. So it was just a matter of training, I think, 7 models or so. Then basically these estimates of these quantiles give you the cumulative distribution function. So this is for every store product combination and for every horizon separately. So it's a lot of things happening, but it's basically just a large for loop, so to speak. And then from this cumulative distribution function, we go to a probability mass function, which is a fairly straightforward transformation. And this then gives you something like, okay, for every possible outcome, this probability that we were looking for. Yeah, next slide, please, Diederik. Yeah. So in terms of implementation details, there was not much exotic things going on. So 7 light GBM models per horizon. Training time was really low. I think I'm not 100%. I did not check, but we could run the whole thing and make an order in a matter of minutes. And this was all fairly straightforward. So in terms of features, also not much special. The usual suspects, legs, moving averages, only for some sort of historical peaks that could be related to, for example, Black Friday kind of things. We included some dummies. to make sure the model performance would not be destroyed by it, because it was for us difficult to include features that would accurately capture it. So to make sure that the model would not learn the wrong relationships, we included some dummies. And yeah, many other features actually. For cross-validation and hyperparameter optimization, which we did a bit like in an ad hoc fashion. We did not take an extremely scientific approach, but we took the last year of data. So that's also not too special. I think what is interesting is that almost all the code was AI generated. So what did that mean? We used Copilot with Cloud in agent mode. I think the takeaway was really that you're much more thinking about what you want and not how you do it. So the time writing code decreases, but reviewing, debugging, and fixing increases. And it was a bit mixed. There were bugs and problems, but overall, I think the takeaway was that this was a positive experience. And then, yeah, this is what I said. So there were some bugs, but also the AI was able to fix it itself. I was amazed by this. You see it on the right-hand side. It's really taking an interactive approach where it says like, oh, perfect. Now let me look at the features.parquet file structure to understand the data better. So it's really came a long way where it is able to really understand also the problem you're working in, querying the results that itself was generated. So yeah, this was an excellent experience for us, and it did work pretty well. Simon, for you to wrap up.
Yes, thanks, Ruben. So I think we had a few takeaways. One was that that's kind of pure approach that we had, not having parameters, not having any business rules, seemed to work pretty well. On the flip side, when things don't go as well as you'd like, there's not really much to adjust. So you haven't got any parameters to play with. So that's maybe something, yeah, that we took away. I think, as Ruben said now, it was really striking how effective vibe coding was. And I think that the one big caveat that I would add is you have to know what you want, and you have to also know how to kind of interpret, review those results. Otherwise, you can definitely get in the mess. Then, yeah, one thing which struck me particularly was how variable the costs were for everyone, actually, from week to week. And I was looking at the standard deviation of the costs over the week, and I noticed our solution, we came fifth, but we had the lowest variance. So I kind of thought that was an interesting one, the lowest variance of the cost week on week, order on order. And then just as a last note, I think it was really nice having this competition focused on a problem which is much closer to a real world business problem. And I'd like to thank the sponsors and Nicola for organizing. It was great. We really enjoyed it.
Thank you so much. Thank you so much. It was an amazing presentation. I think you just gave a masterclass in how probabilistic forecasts work together with inventory. We'll see later if some other people use that. As a bit of a background, many people, not so many, but we had different teams using probabilistic forecasts. We had team using quintiles. We had team using mean forecast. We have a few teams, I'm sure, not using any type of forecast. So what's amazing in VN2 is the diversity of the method used. Actually, for me, it's a real tough nut to crack, to just try to segment what people have been doing, because I'm trying myself to write an article on that. Thank you so much for this super interesting presentation. I realized something while you were doing the presentation. At first, no one was asking questions because I think everyone was so focused on what you were saying. And then you show one slide, and then we had so much reaction from the crowd. It's the slide of agentic AI that you use to code most of the forecasting model. So I'm not reading live the question now, but I'm sure that many people were kind of impressed, amazed, or had question about that. So would you mind to share a bit more? Maybe a question on my side is, it looks like the way you describe it, vibe coding forecasting worked for you, but you didn't use it for the inventory model. Maybe could you give us some hint on why you decided to manually do the inventory part, but vibe code the forecasting part?
Yeah, there's no satisfying answer to that. More than I did the forecasting thing, and I was just very receptive to this adventure. And my friend and colleague Diederik, he did more of the policy work, and he also loved the experience of, let's say, building this himself and going through this process of. Also, his code was a lot better than mine, actually. So that is maybe an important takeaway. So it was just a matter of who did it and who used which tools, actually. And yeah, not so it was not. That was all. That was all.
Diederik did use what tool did you use to generate the graphics?
Oh, yeah.
Gemini, the Nano
Gemini,
Banana.
yeah.
The
Then I
infographics.
edited the text a bit myself. Yeah. But I do sometimes use AI coding assistants, but I like to give them very small tasks and then stay more in control myself.
Perfect. Thank you so much for your presentation. That was really a masterclass in how to do this Monte Carlo simulation, probabilistic forecasting. Amazing. Thank you for the chat on this AI. So now please welcome Carlo, who achieved the 4th position. Carlo, feel free to share your screen so you can share your work.
Yes, thank you, Nicholas. So I quickly introduce myself. I'm Carlo Cavalieri from Italy. I'm a statistician, currently data scientist at Tetra Pak, a B2B manufacturing company. I'm passionate about forecasting and interested in supply chain applications. And so I joined VN2, so the first large-scale inventory planning competition to benchmark end-to-end demand and inventory planning against other experts in the industry. For demand forecasting, I also applied the probabilistic method to model the full distribution of possible outcomes instead of a single point estimate. And so this approach gives a more complete view of uncertainty, so to enable more informed decision making. The model that I choose is DeepAR, that is a neural network model that learns patterns and trends from time series data to forecast future demand. And it also handles missing values. So this enables to leveraging the historical stock availability data that was made available. So I excluded the period without inventory, ensuring that the sales data used for training the model accurately reflects the true demand. And DeepAR supports many distributions, including the negative binomial distribution that outputs positive integers and is quite flexible, so ideal for demand forecasting. And from this distribution, I sampled 1,000 trajectories over the next 8 weeks. I could have sampled also only just 100, but of course the data were not that much, so it was feasible to do 1,000. And just on the chart on the right is just an example of 5 demand paths in the top right, and the forecast quantiles in the bottom against the actual demand. So now how did I use this all these 1,000 demand scenarios to make ordering decisions? So I applied a probabilistic inventory model that for each product I consider all the possible order quantities because we didn't have minimum order quantities in this use case. And for every candidate order quantity, I projected the inventory levels using these demand scenarios. So they are projection in the future, right? And so if I had sampled 1,000 scenarios from the DeepAR model, I would get 1,000 projections. You can see 2 examples on the right. So they have different demand values, but the same initial inventory, the same incoming stock in week 1 from the previous orders, and the same quantity that is received in week 3, in this case 50, that is the candidate order quantity, that is the quantity that we are evaluating related to the order that we are placing now at the beginning of week 1 in the example. And for each scenario, I then compute the total cost, including so it's the shortage cost in week 3, so when the order that we placed is received, and the holding cost from week 3 onward, because basically the order that we are placing now, we might also impact the holding cost in the later weeks. So for the shortage cost, it only impacted the week 3 because we will always have future orders in the next weeks. But the holding cost, it might also impact the following weeks if we select a very high order quantity. And one thing is also that this projection also account for the lost sales, the projected lost sales in week 1 and 2, which in this use case, they do not generate back orders. And so we also don't want to order too much to cover already lost demand. And now we basically after we computed like brute force, right, the cost for all the possible for each order quantity and each demand path, then we average those costs across the different the 1000 scenarios in these cases to get an average expected cost. So now that I got this expected cost for each order quantity, of course, we see this pattern, right? That as the order quantity increase, the shortage cost decrease and the holding cost increase. And what we are looking at is the quantity, the order quantity that minimize the total cost, which is in this case 77, and that is the order quantity that we select for the submission. From round 2, I optimized the DPR model, and I took the pre-competition data, and for each set of possible parameters of the DPR model, I generate the forecast and I simulate the decision process, so getting the order quantities for each of the 6 planned orders. And then I evaluate the resulting cost to select the model that minimize them. So no accuracy metric was used for the optimization. So I had a look of probabilistic accuracy metrics later on, and they are highly correlated with the cost, but they were not directly used for the sake of the optimization of the parameters. And this is important because optimizing the model was essential to climbing up to the top 5 positions, because using a forecast-driven inventory policy is really important that the forecast is not biased and is most accurate as possible, and the probabilistic forecasting models are a bit difficult to optimize compared to a model that only predict the average of the demand. And yeah, that's it. So back to you, Nicolas, if there are some questions.
Thank you so much, Carlo, for this explanation. It's amazing. So when we think about it, your solution and the previous one, it boils down to the idea that you made a probabilistic forecast, you simulated what could happen over the lead time and in the future, and you took the best inventory decision possible. I think one of the key difference, well, you use deep AR, the previous team used like GBM, but beyond that, I find one key difference that maybe made you go to the first place is that you try also to understand what would happen with leftover from week 3 to week 4, 5, 6, 7, and 8, as I understand. So your model understood that if you order way too much today, it's not just you're going to face holding costs for 1 week, but you might face holding costs for the future. And as everyone has seen, VN2 is a competition with seasonal data. So you have some peaks, and if you order a lot at the highest point of the season, then you might be left over with things for quite some time. As I see it, I think Tim has a question for you.
Yeah, I was just curious how you created the forecast profiles.
So how did I train the model?
Yes.
Yeah, it's deep. I use the GluonTS library, and I choose the DeepAR model. So you have a set of you need to choose a distribution. In this case, I selected the negative binomial that is the best for demand forecasting. And then you get from this library, you also get already not only the distribution, but you also get the demand path. So you select a forecast horizon, and you get the whatever number of scenarios that you want, and they also take into account the cumulative distribution, so not only the marginal one. So they are able to like understand the trend. And so if like in the next period you have an increased demand, then in the period later you might it might be more likely that you also get higher demand than the average. And so the reason why I choose DeepAR is this feature of the getting the joint distribution over the forecasting horizon. And
Thank you, Carlo. I'm sure that a lot of people are already Googling or looking for DeepAR and Gluon TS thanks to this very good pitch. I will myself go back into it and read a bit more about it right after the call. Carlo, I have a question from someone from the crowd. I will ask it. I think it's just a simplifying question to make sure everyone understood what you did. So I'm going to read the question here, and I love it. So, Carlo, you made an inventory projection for each possible order quantity, for each possible forecasted demand. And as I understand, you forecasted 1,000 different paths. And for each path, you try to compute, well, what's the cost if I order 0, 1, 2, 3, 4, 5 until whatever. Is this correct? That would be a good summary?
Yes, it's perfect. I choose this approach because the brute force, I mean, the data were not that much in this case, so I could try all the possible combination. Of course, in real life, you might have minimum order quantities. And also, if I had generated like 100 path instead of 1,000, I would got similar result. So, but it was possible to do everything here.
Thank you so much, Carlo. Congrats for the fourth position. It's an amazing model. It's very interesting to see this one both being ranked 4th and 5th with very similar approach. So now let's welcome team number 3. We have Philip and Jakob.
Thank you. So yeah, my name is Jakob. I'm a machine learning engineer, and at Fetcher I design complex features to fuel deep learning forecasting engines, which are utilized to optimize pricing for significant revenue uplift. And yeah, I'm not sure if Phil is coming back, but Phil is working as a partner at Atlantic Insights, and he helps organizations improve customer experience and commercial performance from improvements to forecasting, resource planning, and performance analytics. So initially, our goal was to actually have fun and collaborate again, following our VN1 win. We participated with limited time, so we had to make some shortcuts. We decided on a point forecast for ease and used a simulation model to determine the best policies to order stock. We are not inventory planning experts, so we were not sure how well we will do, but we were keen to study the official benchmark and try to beat it. So that was our actually first goal. And the benchmark forecasting model was deseasonalized the product data using this global seasonality. A 13-week moving average was found. Then the expected global seasonality was applied, and the buying policy of the benchmark was based on 4 weeks of forecast. So looking at the historical data to a total level, it was very clear that there were some kind of seasonality. We also saw that in this variation across January to April, and that was very different than the last 3 years. So we had no contextual data helping us to understand this variation. So with lack of extra context, the dataset was challenging for both statistical and machine learning models. So yeah, we started with EDA, and also we assessed the underlying signal across all time series. We also analyzed like some key metrics, and it indicated that this data set is quite forecastable, let's say. So we wanted to first identify the most accurate models to predict the demand 3 weeks ahead to align with the buying window. We measured each candidate's performance, evaluating it from November to March, and this period included these significant seasonal spikes, which made it especially useful because we expected seasonal spikes within the competition window. And to judge the performance, we used mean error and mean absolute error. We used the rolling origin evaluation, and we were very careful to not do any data leakage.
Okay. Now, in this table are the results of our candidate statistical forecasting models on the test set. We found that the benchmark model was very accurate indeed. We performed tests on the benchmark model and found that using 15 weeks in the moving average gave the lowest error on a rolling origin basis on the test set. We conducted further experiments with this model, for example, modeling high demand products with an individual seasonality and by segmenting the products, but neither showed an improvement to the benchmark model. So the seasonally adjusted moving average model made it into our ensemble. But why did the benchmark model perform better than the individual level stats models? Well, the benchmark forecasting model deseasonalized the product data at a global level. After the moving average was found, a global seasonality was reapplied. We saw that at an individual level, the seasonality was weak and unstable. Models using individual seasonality shifted the forecasts away from recent observations.
So yeah, before I start talking about the rationale behind the LightGBM, I would like to highlight the target definition for it. So LightGBM model was designed to forecast cumulative 3-week sales utilizing features based on non-cumulative sales. So the idea was to enable LightGBM to extract historical pattern from past weekly sales data for predicting the next 3 weeks of cumulative sales. So although this data set offered like very little advantage for machine models, there was lack of price information or other meaningful external regressors, which use LightGBM due to its flexibility and speed in executing new ideas, which was very important under time pressure. So yeah, tree-based models possess these very interesting characteristics compared to statistical models, making them quite flexible. So with the right parameters, target transformations, and feature engineering techniques, you can make them behave as desired. And our goal actually was not to build the best tree-based model, but rather to complement our main model, which we thought would under-forecast based on our judgment. And this is why we designed the LightGBM model to consistently over-forecast. So features were heavily engineered to capture seasonal effects. Parameters were selected for small data set size. Target was like designed to enable the model to extrapolate, and asymmetric loss function was applied to force this model to consistently over-forecast.
Now, the starting point for our simulation model was the Python code included in Nicholas's inventory planning book. We adapted this to run over a 12-week test period, looping it across 599 products. Our simulation code calculated stock buys based on forecasts and a specific buying policy. It then calculated end-of-week stock and lost demand, from which it calculated the total competition cost. This cost determined how good a forecast and stock buying combination was. We ignored service levels and fill rate. We placed the benchmark into the simulation and understood its cost over the 12 weeks. With the seasonally adjusted MA model, moving average model, only slightly better than the benchmark model, and with a buying policy based on 3 weeks ahead, multiplied by a factor, we knocked nearly 13% off the benchmark cost. Putting in our ensemble gave us a 14.3% saving. Then we introduced K times RMSE, and we reduced our order by expected lost demand. This brought in a 16.3% saving against benchmark. In our simulations, we found that the more accurate the forecasting model, the lower the cost. This was a strong relationship. This 16.3% benefit was achieved by optimizing against the test set, so we didn't think that we would get this full benefit on the unseen competition data. Now, some of you may be appalled by this, but we found that an Excel worksheet was ideal for the calculation of the weekly order. Here are the forecasts, the order up to level, the net inventory, the lost demand reduction, and the final calculation with rounding. This visual chain of logic gave us a reassurance that interim calculations were working as intended. Anything that looked odd could be checked.
So after we submitted the two orders and we still had no results, we already noticed that the seasonal moving average model was not responsive to some short-term level shifts. And we performed simulations again, and we decided to change the average window from 15 to 9. And the results started to come through. Week 4 was terrible for us. The more responsive model came into effect for week 5, but we were still dealing with some issues from previous week. And after we had made the 4th stock order, we started making some manual adjustments to some odd-looking like GBM forecasts for certain products. And also further simulations led us to move the value of K, the RMSE factor, from 0.245 to above 0.3. And these changes helped improve our performance significantly in the final 2 rounds. And this is where we were lifted from outside the top 20 up to the 3rd place with over 13% benefit on the benchmark. Next slide, please. So takeaways. So first takeaway, I think, is that the benchmark forecasting method, simple as it was, it performed very well and proved surprisingly hard to beat. On the other hand, the benchmark stock buying policy of 4 weeks was considerably easier to improve upon. Another one about tree-based models. So you can tweak your tree-based models to behave as you desire. This flexibility is really useful to create ensembles. We found also a strong relationship. The better the forecast accuracy, the lower the total cost. Simulations were very valuable to save testing and some techniques and policies. The 3 weeks plus K times RMSE approach was more effective than just a simple multiplicative factor. And the lost demand adjustment provides some extra benefit. And together, these lessons helped us to identify approaches that were both accurate and practical in this competitive setting. So this was tremendous learning experience for both of us. I had so much fun together with Phil. So congratulations to all the winners, and thank you again, Nicholas, and sponsors.
Jacob, Philip, thank you so much for your presentation. I loved it. I was deep into your presentation. A few words about what you share first, for people who do not know you. The 2 of you already won VN1, the forecasting competition we had last year. And what's amazing about your team is that you never met in real life. You're not colleagues. You are not used to work together. You just met for VN1, and then you decided to work together for VN2 again, with a solution that again brought together statistical model and light GBM together, exactly as you did for VN1. It worked for VN1. It worked again for VN2. It's amazing. I appreciate also that you use this lost sales or lost demand trick. It relates to what I introduced regarding the benchmark, that just using the net inventory level might not work because of shortages. So you use this trick as well. This is really great. Thank you so much for the presentation, for sharing that, for being there together as a team. Again, I think it's a very good message for the community that we can bring different people into solutions. Last word on my side, I love it that you also used Excel. And when we designed the competition, I wanted that it was big enough that we could use a bit of machine learning, but small enough that some people could play with Excel. And we had within the top 20 people using only Excel. You partially rely on Excel, and that's great. And I want people to know here in the audience that even if you're not a Python master wizard, you can go to Excel and run the solution on Excel, and it will work. Let me just take a look at the question to make sure I got an interesting question here. Again from Juan. Juan is asking, can you give us a bit more clues about the difference between this global seasonality you talked about and I talked about versus the local seasonality?
Yes, in terms of the global seasonality, and yeah, when we looked at the historical data, there was lots of level shifts, and there was particularly on the smaller products, there was no useful seasonality in the history that those individual models could use. So applying the global seasonality was just ideal for us.
Excellent. To rephrase
Okay,
it maybe slightly differently.
you can find out how that works by looking at Nicholas's benchmark code.
Yeah, to rephrase that maybe slightly differently, if you look at product one by one, it's not sure if we can see any seasonality, because some of the sales are so low and so sporadic that you don't know if it's seasonality or if you were just lucky with sales. But once you look at it from a higher level, if you aggregate everything together, then you start to see seasonal patterns. Now, one of the drawbacks of doing that is that you put everything in the same bucket and you don't know if every product behaves the same or not. So of course that can also come with some issues.
Yeah, but we did do some experiments by looking at the bigger, the higher demand products and treating them individually, and we found that it did not reduce the error.
Overfitting. Excellent. Let's now move on to the next solution.
Well, first of all, thanks, Nicholas, for hosting the competition. This has been very entertaining and a very good learning experience. So I'm going to talk about my deep reinforcement learning approach for the inventory control competition. So just a quick overview of myself. I'm a fifth-year PhD student at the Business School at Columbia. The program is called Decision, Risk, and Operation. It's basically an operations research program, and I'm specializing in reinforcement learning. And for my thesis, I have mostly been developing deep reinforcement learning applications for inventory control. In particular, I don't have world experience with forecasting, and I highlight this not to show off, but to highlight that I think that reinforcement learning can help a lot in the optimization part of inventory control. So I'm sure that people that have more forecasting experience than me can use my model and improve it a lot. So I would encourage you to do that. And yeah, I joined VN2 just to try these methods that I've been working on during my PhD and see whether they actually work in practice or not, and do it so in a competitive environment. So first, I want to give some overview of how reinforcement learning is different to forecasting. So my understanding is that a typical approach to inventory management would be to first train a model that is going to predict, let's say, the immediate demand or a probability distribution of demand. And based on that, then you're going to solve some underlying optimization problem. But once you have a forecast, it is actually not clear even how to phrase that optimization problem, right? Because you don't just have to optimize for costs. Like short-term costs, you actually have to be forward-looking and see how your actions affect you for many periods from now. And now reinforcement learning, what it does is that it takes the information that you have, and it doesn't produce a forecast, but it directly tries to optimize for long-run cost. In this case, it's going to be, you just want to take the actions that are going to maximize profit. To make this more tangible, this is one example of how you could probably do this in two phases, how you would forecast then optimize. What you would do is that first you would train, let's say, a machine learning model that you're going to give it some information about recent demand, for example, upcoming holidays or promotions running, and whatever feature you engineered for your data set. And you're going to train some machine learning model to forecast demand. And that can be a probabilistic forecast or just a point estimate. But now, how would you turn that into an actual order? One way to do it would be to take the product economics. So for example, how much does it cost to keep a unit in stock, and how at what price do you sell the units? And you could target a quantile, for example. And so then you would merge, right, the information from the forecasting with the information from the optimization branch, and you would and based on that you would define an order quantity. So for example, if the quantile that you target is the 90% quantile, you would get the forecast demand and order up to the 90% of the demand forecast. Now, reinforcement learning, what it promises is to, in a way, bypass the forecasting part, and you would simply gather all the information that you have and pass it, for example, to your neural network. So in this case, what you would do is pass all the information that you pass to your forecasting model, be it recent demand, upcoming holidays, planned promotions, or whatever signals you think are important for a forecasting model. You would give this to your neural network. You would also give it the product economics, so the prices and cost, and the current state of inventory. So how many units you currently have on stock and how many units are going to arrive in the future. You're going to pass it to this neural network, and it should directly output how much to order, right? So you don't go through the intermediate forecasting step. Now, I'm going to put an asterisk on this because my solution actually does use forecast, right? Like, I think the way I have basically the data set up, like the features that I built for forecasting are not very good. Like the signals that I passed to my agent were not very good. So in the end, I did use an LGBM to produce like quantile forecast of future demand. And I pass those signals to the neural network that defines orders. So what is reinforcement learning? What it does is it optimizes a policy. So you optimize basically a rule that maps a state, right? Let's say information to an action. So in inventory control, the actions are the order quantities, and the state, right? The information that you're going to pass to the neural network is, as I said, everything that you would usually pass to a forecasting machine learning model, plus everything else that is important, like prices and the state of inventory. And so then you would have like this iterative procedure where your neural network is going to tell you how much to order. You're going to pass that information to a simulator, where the simulator is going to be your code that in a way is trying to simulate what you think the real world looks like. In this case, it's just going to, well, you're going to tell it how much you ordered. The simulator is going to tell you what the actual demand was, and it's going to return the state of demand and the next demands as well. And you would do this for many periods. And then your objective is to, let's assume that you have a neural network that has tunable parameters, right? The weights and biases of the neural network. And your goal is to tweak these parameters, these knobs, so as to minimize total cost or maximize profit. And then again, this simulator, you would build it with a data set of historical demand. So this is like a high-level overview of how you would train an RL agent, right? A neural network for RL. First of all, well, let's imagine that we have like 1,000 products. You would usually train in batches. So in each batch, I would select, let's say, 100 products, right? And for each product, I'm going to have this time series of demand, let's say, for 2 years. And then for the current policy that I have, right? So the neural network with the current weights, what you're going to do is that you're going to simulate what would happen under your current policy. So for those 100 products, for those 2 years, you're simply going to use this neural network in this iterative fashion, passing ordering actions to the simulator and the simulator returning the next state. And that is going to tell you how you would have done with that policy. So basically, what's the profit on the 2 years of those 100 products if you apply the current neural network that you have. Now, the magic here is that you as an engineer, you only have to code the simulator, right? The rules that define the logic of the world. But then in order to update the parameters of the neural network, to calculate, let's say, a derivative, a gradient, you're not going to do math yourself, but you're going to call a machine learning library. So for example, in this case, I use PyTorch, right? So I have the simulator, I simulated my policy, and then I call PyTorch, and PyTorch calculates a gradient. And the gradient basically tells me, under your current neural network policy, your profit was X. If you tweak the parameters, right, like the weights of the neural network just a bit in this direction, you're going to improve total profit. So that's basically the gradient. Okay, so you're going to repeat this many times. So, right, I'm going to simulate a policy for many products and many periods. I'm going to call PyTorch, and PyTorch is going to tell me change the weights of the neural network in this direction just a bit, and I can guarantee if you move it a small enough amount that the profit is going to increase. And you just repeat it many times until you are happy with what you get. Now, well, my actual solution, as I said, like I think that the features that I was using for let's say for the underlying forecasting part was not very good. So what I actually did was I trained an LGBM model using ChatGPT. What I did was I trained one LGBM model for 10 different quantities of cumulative demand for 3 weeks, right? So in the end, there's like 30 different LGBM models. And yeah, I predicted cumulative demand. So the demand this week, then I predicted the demand of this week plus next week, and also the same plus the demand 2 weeks from now. So I have these 30 numbers, and when I train the neural network in the simulator, for each product, I will pass these 30 numbers to the neural network, right? So the neural network, in a way, had this very good information about what the demand for each product could look like in the future. And then after I want to highlight here that I use it. I trained it using ChatGPT because I don't have a lot of experience with this. It does seem that ChatGPT did a good job here, but like I'm sure that people with experience in forecasting can do a better job than I did. And then, yes, I explained, I trained the neural network with the inputs, the outputs from the LGBM model plus the state of inventory, right? So how many units you have on stock and how many units are going to arrive next week. And I used all products for training, but I held out like the last 8 weeks of data for validation. So basically, I used early stopping, and I freeze the model of the neural networks when you minimize the cost or you maximize the profits in these 8 out of sample weeks. And well, if you want to read a bit more about like the work itself, like this QR code on the top is a link to our paper where we use this for many inventory control models. And on the lower QR code, you have access to our repo. That's from the paper. I did another repo especially for the VN2 competition. So if you want to try, like, let's say this RL approach using your forecasting model of preference, you are like, I encourage you to do so.
Thank you so much, Matthias, for this presentation. It's very, very, very interesting. I have a few questions and remarks. Your solution is so unique. I think you're the only one who tried reinforcement learning, which is, I guess, the most high-tech solution that anyone used here. So first, congrats for that. I think we met by email a few years ago, and you told me about your research, and I actually doubted. I was doubting the idea of the added value of reinforcement learning versus simpler methods, and you proved me wrong and the whole community wrong that reinforcement learning works. You made it work, and it's amazing. You're the only person, to the best of my knowledge, who tried this out, and it worked. For the audience, if you don't know the difference of score in between the winning solution and the second solution here, I think it's 1.2 euro out of 3,800 euro of total score. So the gap between these solutions is extremely tight. It's amazing. Congrats, Matthias, for this amazing, unique model. Congrats for making, for delivering such a thing and explaining that to us. Let's maybe move on then with the winning solution of VN2. Bartosz, if you can take your screen, so please welcome on the virtual stage Bartosz, who won VN2, and he will share his solution.
Okay, so hello everyone. Hi, fellow forecasters. My name is Bartosz Szabłowski, and day to day I do a job that I think and I know is also my main passion, because I work as a data scientist specializing in time series and forecasting. I have been working on forecasting problems for a bit more than 5 years now, basically since the very beginning of my career. Right now, I am a data science tech lead at Schneider Electric, where I'm working for a global forecasting system used by our finance teams. Before that, I worked at Nestle on an operational sellout selling forecasting solution for the European market. Also, I see here some of my colleagues from my current and previous company, and I'm happy to that. And also I have delivered some freelance projects around time series for supply chain, retail, or even stock market use cases. And let's move now to my actual solution. And I split it into 2 stages, which I think is very natural design. So I separate the forecast model from the decision policy that uses this forecast. So the stage 1 is the model what generate point forecast, what is something different from the previous presenters for the next 3 weeks. It uses historical sales and also an availability flag. So the model knows which weeks were affected by stockouts. Stage 2 is the ordering policy. So it takes the forecast from the previous stage and also the current inventory, what is on-hand inventory, and also in-transit deliveries for week +1 and week +2. So the objective is very classic. We want to keep the inventory as low as possible, but without generating expensive stockouts. Even though I talk about 2 components, they are strongly connected. So a better forecast should enable a better, more precise ordering policy. In the previous slide, we saw the high-level methodology. So now let's go into the first stage. What is the forecasting part? I use a direct multi-step horizon strategy. It means that for each horizon, I have a separated estimator. And the base estimator is cut boost, also something different based on the previous presenters. And I use this cut boost as a global model. So it is trained on all store product series together, and at prediction time, it still gives a separate forecast for each combination, of course. And the choice of the estimator matters, but many participants could pick the same estimator and still end up with very different scores. What we already saw, a lot of competitors took LightGBM, but their results were different. So the estimator is only as good as features we fit into it. So the key piece here is feature engineering, what translates different patterns through features. And in a global model, we have a single model for all time series, which are very different time series. So this feature must be able to handle a range of behavior like intermittent versus regular demand, stable trend, no trend, or trend changing over time, seasonality, no seasonality, drifting seasonality, and of course, the model needs to include this stockouts period in history. A global model doesn't matter, it is machine learning or deep learning, can be extremely powerful, but we need to allow it to be powerful as the data scientists. And for machine learning, we are able to do it, make this global model powerful through features engineering. And when we look into my methodology, we can structure the feature engineering into 3 main groups. The first group I would call created features, of course, but I would call them like behavior features. So these are created variables that describe plenty of different behaviors and allow the model to adapt to these different patterns inside of time series or different structure. And the second group on the right side is scaling. So here the goal is to shift the model's attention from the absolute level to patterns for time series. So different series can live on different scales. So for one product, the average weekly sales, let's say, can be 10 units, but another can be 200. So if we don't normalize that, scale that, the model wastes the capacity learning the scale instead of learning the structure, patterns inside of time series. So for each store product, I call it dynamic scale factor based on a rolling 53 window using only weeks without stockouts. So for this data set, a simple mean is absolutely enough. But of course, there is a lot of other options like using quantiles, by scaling through exponential smoothing, etc. And this scale factor is then used to scale our targets, but also it is used to scale all target-based features. And the third group is time decay weights. So during training, I apply it, and observation from the last year received the highest weight. And as we go back further back, the weights decay. So we can say that the model listens much more closely to the recent behavior, because we can have for our data set something what is called data drift. Okay, and I already described you the first stage, so let's move to the second stage, how I translate or how I turn the forecast into the orders. And for easier explanation to you, I split into 4 steps. The first step is orders itself. The second step is project inventory to start of week +3. In other words, what is left after week +2. The logic is simple. So we start from the current on-hand stock plus in-transit delivery for week +1, subtract the forecasted demand for week +1. If something left, then it becomes the starting inventory for week +2. Then we add the in-transit delivery for week +2 and subtract the forecasted demand for week +2. And if something left, it is our projected inventory for week +3. Why? Because it cannot be negative, of course. It needs to be positive value. Then we have the third step, what is cost-aware target stock for week +3. So now let's define what the target level of the stock we would like to have after order generation. So in the competition, we have shortage cost, which is 1, and also we have a holding cost, which is equal to 0.2. And based on that, I compute something what I called here service level, what is shortage cost divided by shortage cost plus holding cost is around 0.83. So we would like to cover the 83rd percentile of the demand distribution. So I assume that forecast errors, not forecast itself, I'm talking about the forecast errors, are approximately normally distributed with mean close to 0. It means that our forecast is not biased. So for a service level of 0.83, the corresponding z-score of the standard normal is about 0.97. So it means that the 83rd percentile is about 1 standard deviation above the mean, right? And we still need a simple proxy for uncertainty, and I defined it like sigma is equal phi multiplied by square root of the forecast, and this phi is a single parameter optimized on the validation set. And we can think about target stock for week +3 as a forecast from the model itself plus safety buffer, where the safety buffer is directly linked to the cost ratio, time series scale, and optimized on validation set. This cost-aware target stock is really simple, but still it contains these 3 things. Like it includes the cost ratio, time series scale, and it is optimized also on validation set as other time series model hyperparameters. And also the order rule, once we know the projected inventory at the start of week +3 and the target stock, the order is the max from target minus projected inventory or 0. Why? Because in practice, for many store product combination, this value is exactly 0, which we actually want, because if projected stock is already above the target, the best decision is not to order anything, because the order cannot be negative, right? Okay, and overall, it delivered about the 13% cost reduction versus the baseline. And as Nicolas mentioned, even this baseline was simple, wasn't trivial to beat for many participants. And also on the chart, you can see one example time series with historical demand and simulated inventory level at the start of each week for the last 18 weeks in the simulation, what simulation I did locally. And you can see that inventory stayed slightly above historical demand. So we protect ourselves against stock out, but we don't drift into overstocking. So this is exactly what we want in real production system. Fewer empty shelves without freezing capital in the warehouse or risking product expiring. And okay, here you can find some of my key takeaways. And also I would like to congratulate to other winners. Thank you for your attention. thank you organizers for designing such a great time series challenge, and I hope we will also meet at some conferences like the International Symposium on Forecasting or other ones. Thanks again.
Thank you so much, Bartosz. So you see a lot of applause, virtual applause for you. Thank you so much for sharing your solution. Congrats on your solution. I would have a question, but before that, I think you gave a real masterclass in how to create features for Cat Boost and apply GBM. Ruben, I really appreciated your joke on the chat. You gave an amazing masterclass on how to make a feature engineering for light GBM forecasting model. I wish none of my competitors ever see this slide. It's amazing. I have one question, if you don't mind going one or two slides back when you discuss your model for safety stock. I see I'm not the only one raising some question there. Let me just try to rephrase it just to make sure I understand what you did. So you started by saying that you want your service level to be 83%. Then you transformed that into this quantile that is a multiplication of 97. And then that's the ZQ. So ZQ is basically 0.97 as like just a factor. And then for this kind of safety uncertainty proxy, as I understand, you take the square root of the forecast. So like the forecast is 50 pieces, you take square root of 50. And
Yes.
you multiply this times another constant that you optimize throughout simulation. So this constant could be, I don't know, 1.2 or whatever, that you optimize against the whole data. So you take, this is my forecast for week 3, this is the square root of the forecast, and I multiply the square root by this constant I optimized. Is this a good summary?
Yeah, but what I did, I optimized this phi value for all combinations. So it's not phi value.
It's one by one.
Other, yes, it's only one value. So at the end, I think this phi value was around 0.1, something like that. But so it's just one single parameter optimized for all combinations, what I generate forecast and make decision of the orders.
Excellent. So it's really been optimized locally, and you have a different factor for each product, and this multiplies the square root of the forecast.
Yes, exactly.
Clear. Thank you so much, Bartosz. Congrats again. It was an amazing presentation on feature engineering for sure. Congrats on your inventory model. I'm really impressed here to see the amount of different solution we have. When you look at the 5 winning solution and the other solution in the top 10, we have very, very different solution. That's amazing. So it's really not like we could say this is the one and only way to make inventory right. There are so many different ways. It's very, very interesting. Maybe Fabrizio, team, would you have some question to share here with the winning teams?
Yes, I would like to ask a question, and I'll get ahead of you, Tim, just because my question is probably going to be dumber than yours because I'm not technical and I'm solving a much broader problem. I have to choose one person to ask the question for so that we don't spend too much time. So I'll choose Philip and Jacob just because they were winners in the first in these first 2 competitions. So how much impact do you think the data? Okay, so we have different problems at Fleeper. The first is that the data that comes in a way that is not explainable, and we don't have the chance to sit for months with a customer to organize the data and clean the data and then process the data, the clean data. So we have to do a lot of work on the data. Then we have the forecasting itself, which is the machine that we use to forecast the sales. And then we have all the optimization algorithms to actually define what is the replenishment suggestions. And we also define sales adjustment suggestions if you should add promotions or reduce advertising, for example. In these 3 fronts, how do you see what is the most challenging for you to solve with the technology that you have today?
Well, I would say that the repair of the data would be by far the most challenging thing because it is so different for every application, and also it's the area which gives the biggest opportunity. Because I would far sooner apply a simple forecasting model to great data than complex model to poor data.
And a follow-on question, then quick follow-on question. with like if you had in 30 seconds to define how to solve this at scale, what ideas would you have for us? Because I agree with you, that's the biggest challenge we have too.
I'd want to take this offline maybe. Can I answer this question off the top of my head? Maybe Jakob has a suggestion.
No, I think this is a question that we can talk for hours, but I think like generally it's good to start with the assessment if your data is even forecastable at the beginning. So using some kind of coefficients or checks. Different coefficients works for different data sets, but generally some kind of sanity checks like auto-correlation coefficients or maybe some forecastability metrics is a good start, because if there is a very low signal in your data set, it's better to aim for very simple models. And then it comes back to the benchmarking topic, because I really think that rigorous benchmarking is crucial on whatever data set you're using. Is it forecastable? Is it not forecastable? Is it big? Is it small? I think that the benchmarking is pretty often forgotten, and it shouldn't be.
Okay, thanks. I just to explain why I asked this question, we are all here, most of the people here are technical people thinking about breakthrough solutions in data science related fields, but ultimately the quality of the data is and will always be the main challenge to be solved first. I talk a lot about that with Nicholas. So just as a lesson to the people who are entering this segment and probably watching this webinar, focus on data first. There's no magic solution if you don't have the right data. So that's why I asked this question. Thanks, Nicholas. Thanks, everybody.
You're welcome, Patricio. Maybe Tim, a last question.
I'll tell you the question I was going to ask, and then I'm going to change my question and suggest people type it in. The question I was going to ask is, when we were designing the competition, we were thinking how complex to make this, and we chose to not make it too complicated because we wanted people to be able to use Excel. We wanted it to be accessible to lots of participants. But the question I was going to ask is, if you had to simulate available manufacturing and lane capacity, supplier lead times, et cetera, if you had a much more complicated network, what changes would you have made to your approach? But we don't have time to answer that. So my question instead is, what is the next competition that you would like to see? Just like Fabricio, we want to sponsor more competitions like this and help the community learn from each other. So curious what another interesting competition would be that you'd want to see.
I think, Tim, that's a great question for the whole crowd in the audience as well. So I guess everyone can type an answer. I will for sure be reading your comments as well. Maybe a word then, Tim, on some of the design of VN2. Many people asked and will in the future still ask me, why don't we have purchasing costs? Why don't we have minimal ordering quantities and things like that? It's not just a constraint for me on complexity. So first, purchasing cost MOQ are totally realistic. I'm not saying that this does not exist and it's not important. It is. But to include that in a competition would create edge effects on the last rounds. It would try to push people not to make any order because the MOQ would be big. And I wanted to avoid that. But as you said, we have to find next. So for VN3, what do we include? How should we do it? I'm still digesting personally VN2. It's so much content. The solution is so diverse. It's not like we can say this is the one thing that works. Instead, I'm really trying to understand the mindset of the people here who won and the other people in the top 10 or 15. What was the mindset? What the kind of framework did they use to win? If I can use that maybe to conclude on my slide with one last slide, if I can share my screen here, just give me a sec. I will in the following weeks come back with some notes I took on, I said, the winning solution, trying to come up with the frameworks and the main ideas. But what I see over and over is winning people have a very strong framework, a mindset to test and optimize things. They don't come saying, I had a model, I didn't touch the feature, I didn't touch the weight, I didn't touch anything, I just used it and it worked. People come up with, well, I had this idea, I tweaked it, I optimized it, I tried to backtest it, and so on. And over time, it grew into the final solution we see. We also see that, and we don't see that on every solution, but in many solutions in the top, people try to bring different models together. And it's, in terms of forecasting, it adds a lot of value. I think my key message for this competition to everyone in the audience is give it a try. The data is available. I'm also happy I will find a way to share a way for you to replay the competition using some Python code. So you don't just have the sales data, you can really use the simulator yourself to give it a try, to try your own approach. I really want this VN2 to be part of the something in the community for everyone to give it a try. As said, when we started, winning a competition after the competition is much easier than winning the competition during the competition, but still it's a lot of fun. I'm looking forward to see what people will come up with on this very data set. Look, everyone, it's been an hour and a half. It was a pleasure for me to host everyone here, the winners, the sponsor, Fabricio team. It's such a pleasure to organize VN2 with you. I'm sure we'll all stay in touch on LinkedIn for sure. Feel free to ask a few more questions in the chat. I'm sure some people will still provide answer. Thank you all, everyone here, for being part of this community. It's such a good vibe, but also a content-rich community. It's amazing because at the end it was a competition, but we're having so much fun discussing all these models. So from the bottom of my heart, thank you so much for being part of this. Have a great time, everyone. It was a pleasure for me to host that with these two amazing sponsors, Tim and Fabricio. It's always amazing to discuss the model with the winning teams. Congrats to everyone. Thank you, and thank you so much for being part of this.